Okay, so section 1.3, we are looking at some graphing techniques of functions. In the past, you guys have graphed just by finding points that lie on the graph of a function. So basically choosing values for x that are within the domain of the function and then finding the y-coordinates that go with them. Now we're going to look at how we can graph different functions from the perspective of using translations and transformations. And we're going to look at graphing functions that we're already somewhat familiar with. But the cool thing is we're going to be able to take this technique of using translations and transformations to also graph functions that we study down the line in this class. So I'm breaking this section into two parts. So the first part, we're going to be looking at graphing vertical and horizontal translation. So that's vertical and horizontal shifts. So if the graph of a particular function is just kind of moved around the xy plane, up, down, left, right. And then we're also going to look at applying reflections, so horizontal and vertical reflections. Now, horizontal and vertical reflections are actually a type of transformation. However, I think that reflections go nicely following talking about translations, so vertical and horizontal translations. And then in section part 2, or in part 2 of section 1.3, we're going to actually talk about transformations, so vertical and horizontal stretch and shrink. So when we're graphing a function using translations and transformations, we need to think about the function's parent function. And the parent function is basically like the simplest form of that function. And I told you guys about, or I showed you about those 9 common functions that I'm expecting you to be familiar with that were in section 1.2. And you should be familiar with some of the points on each of those graphs, so that then when you're trying to graph more complicated functions using translations and transformations, you're thinking about shifting those points or reflecting those points, or stretching or shrinking those points. Okay, so vertical shifts happen when you're adding or subtracting a constant to the parent function. So if the equation that you're given to graph has the parent function and then plus some constant or minus some constant, what that means is that in order for the new function, the function that has been vertically shifted, to have the same x-coordinate as the parent function, we have to add or subtract whatever that constant is to each of the y-coordinates for the x-coordinate to be the same. Vertical shifts, I think, are pretty easy to wrap your brain around. Basically, you're adding or subtracting a value to each of the y-coordinates. And that will either move the graph up in the xy plane or move it down. Anything horizontal usually takes me just an extra second to kind of wrap my brain around. So horizontal shifts happen if we do something to the x of the parent function. So like if we have f of x plus c, that's actually shifting the parent function to the left c units, which is kind of the opposite of what I would initially think, seeing adding c, right? You think if you're adding a value, you're going to the right. But the reason this happens is that when we add a constant, so c is a positive constant, to each of the x values, in order for the function to have the same y-coordinate as the parent function, we have to do the opposite then to the x-coordinate in order for the function to have the same output. So if we add a constant to each of the x values, then we're going to have to subtract whatever, like let's say we're adding 2 to each of the x coordinates. Then we're going to need to subtract 2 to each of those x coordinates, or from each of those x coordinates, in order to have the same y coordinate as the parent function. And then if we are subtracting c, that's going to end up being a shift to the right, because you would have to add c in order to have the same y coordinate as the parent function. I like to start off by just thinking about kind of the most simplest function of all. So y equals to x. And I'm going to graph y equals to x here. So that's a line that has y-intercept at the origin, a slope of positive 1. And I want us to think about graphing a shifted version of this function, but from 2 different perspectives. So what I have just graphed is y equals to x. Now let's think about, I'm going to write 2 equations here. So I'm going to write the equation y equals to x plus 4. And then I'm also going to write the equation. So here's y equals to, in parentheses, x plus 4. And what that parentheses does is it indicates that I'm adding 4 to the x, to the input. So what this top equation without the parentheses represents is actually a vertical shift up 4 units, where basically we're adding 4 to each of the y coordinates. So the point that was at the origin would then be at 0, 4. The point that was at 1, 1 would be at 1, 5, and then 2, 6. We're adding 4 to each of the y coordinates of the points that we have graphed. So that's how we would think about applying a vertical shift. We get y equals x plus 4. Now, the reason I like to start with this example is you guys know that the parentheses there are not really necessary. However, when I have them written that way, where we're thinking about adding 4 to each x coordinate, meaning to have the same y coordinate, we would need to subtract 4. This ends up being a horizontal shift to the left. So this was a vertical shift up 4. To the parent function. And then this would be a horizontal shift left 4. So we could think about, here I'm going to change this to be green. So the point that's at the origin, in order to have the same y coordinate, we would shift to the left 4 units. And we end up at negative 4, 0. The point that's at 1, 1, we subtract 4 to have that same y coordinate of 1. So we end up at negative 3, 1. And just think about shifting each of these points to the left 4. So it's just graphing from a horizontal, thinking of this as a horizontal shift instead of a vertical shift, which we're able, this does not happen for every function. Like a vertical shift does not always end up looking like a different horizontal shift. However, just starting and kind of thinking about graphing this new graph or new equation from 2 different perspectives. So thinking about the vertical shift versus thinking about the horizontal shift. So let's look at some more examples. Now notice that for these 4 equations, they all have the same parent function. And the parent function here would be the absolute value of x. Y equals to the absolute value of x. So let's go ahead and graph the absolute value of x. Okay, so that would be our parent function. Now, if we want to graph g of x, that plus 4 is going to be a vertical shift up 4 units. Every point that lies on the parent function will be shifted up 4 units. And it's helpful if you're familiar with the parent function, which you should be, just thinking about shifting a few of those points, like the points that are about the origin. And end up a little bit off unit. Okay, so this would be g of x. H of x equals to absolute value of x minus 6. So that is also another vertical shift, but it's a vertical shift down 6 units. So we end up subtracting 6 from each of the y coordinates of the parent function. Again, I just think about shifting a few of those points that are on the parent function. And then that gives me h of x. Okay, notice for the function capital F of x equals to the absolute value of x plus 3, that plus 3 is happening inside the absolute value bars. That indicates that there is a horizontal shift to the left 3. We're having to subtract 3 from each of the x coordinates in order to have the same y coordinate. Okay, so the point that was at the origin is now at negative 3, 0. The point that's at 1, 1 would now be at negative 2, 1. The point that was at negative 1, 1 would be at negative 4, 1, and so on. So that's capital F of x. Oops. And let's use the bright blue. Okay, capital G of x. I can see that minus 5 is inside the absolute value bars. I'm going to actually rewrite that as absolute value of x minus 5, so that I can see that's a horizontal shift right 5 units. We're having to add 5 to each x coordinate of the parent function in order to have the same y coordinate as the parent function. So the point that's at the origin ends up at 5, 0. The point that's at negative 1, 1 would end up at 4, 1. The point that was at 1, 1 would end up at 6, 1, and so on. And when you're graphing multiple graphs in the same xy plane, very important to label those graphs. Now, whenever we apply horizontal or vertical shifts, we sometimes end up adjusting or changing, the domain or range of the parent function. So if we look at the function g of x, got stuck. There we go. If I look at the function g of x, the parent function for g of x would be y equals to the square root of x. Okay, and the plus 4, notice, is underneath the radical. That means that the parent function, to end up with the function g of x, there is a horizontal shift to the left 4 units. To the square root of x. Square root of x, remember, it has a point at the origin, 0, 0. So here, I'll draw the parent function. We have 0, 0, 1, 1, 4, 2, 9, 3. Those are the points that I always think about for the parent function. So this would be y equals square root of x. And so the shifted function, left 4 units, 0, 0 would end up at negative 4, 0. 1, 1 would end up at negative 3, 1. 4, 2 would end up at 0, 2. And then 9, 3 would end up at 5, 5, 3. So nothing has happened to the shape of the graph of the parent function to end up with g of x. Each point has just been shifted to the left 4 units. So let's look at the domain and range. So the domain of the square root of x is from 0 to infinity. And the range is also from 0 to infinity. The domain of g of x, just looking at the graph, it looks like is actually from negative 4 to infinity, and the range would be from 0 to infinity. So the range stayed the same with this horizontal shift, but the domain ends up being shifted to the left 4 units, so that it's negative 4 to infinity. And the parent function for h of x would be y equals x squared. If I graph that, I know the point at the origin, which is the vertex, 1, 1, negative 1, 1, 2, 4, negative 2, 4, 3, 9, negative 3, 9. You do not always have to graph the parent function. I'm just graphing them here for the lesson. And that -3, the -3 is not in parentheses being squared. So that -3 is actually a vertical shift down 3 units. So each point on the parent function is being shifted down 3. I'll use green. So the point that was at the origin will be at 0, negative 3. 1, 1 is down at 1, negative 2. Negative 1, 1 would be at negative 1, negative 2. And then either you're just familiar with kind of where the other points should be, or you can think about each of those as being shifted down 3 units from the parent function. Now, the domain of the parent function is all real numbers. The range is from 0 to infinity. The domain of the shifted function, h, is still all real numbers, but the range is going to be -3 to infinity. So reading the graph from bottom to top, it looks like the range ends up being shifted down with that vertical shift. And then sometimes there's multiple translations that are applied to the parent function. So how about h of x? You can read the equation from left to right. When we're just dealing with translations, we can read from left to right. The vertical shift should come last. So if the vertical shift is written in a different way, like if we saw this as 3 plus the quantity x minus 1 squared, that's fine. However, when we also are dealing with transformations, we want to make sure to apply the vertical shift last. So we would rewrite it the way that we have been given the equation as h of x equals to the quantity x minus 1 squared plus 3. That minus 1 is going to be a horizontal, I wonder where that came back. Okay, so that minus 1 is going to actually be a horizontal shift. Can't spell right now. Horizontal shift right 1 unit. And then the plus 3 is going to be a vertical shift up 3 units. And the parent function here for h of x is y equals x squared. So the point that's at the origin, which is the vertex, is going up, it's going right 1 and then up 3. And then the point that was at 1, 1 would go to the right 1 and up 3. The point that was at -1, 1 would go right 1, up 3. And the point that was at 2, 4 could go right 1, up 3. And the point that was at -2, 4 goes right 1, up 3. So you can just think about applying those shifts to each of the points that's from the parent function. Sorry, my Apple Pencil's being a little funky. Okay, g of x, the parent function would be the square root of x. Okay, that plus 2 is underneath the radical, so that's going to be a horizontal shift left 2 units. And then the minus 4 is a vertical shift down 4 units. So the point that would, for the parent function, is at the origin, goes left 2, down 4, landing me at -2, -4. The point that would be at 1, 1, if I go left 2, down 4, lands me at -1, -3. And then from there, I either know the shape, like if I go 4 over to the right, and then I can go up 2, and then if I go over 9 and up 2, or you can just think about, okay, the point that was at 9, 3 is going left 2, and then down 4, 1, 2, 3, 4, and lands me at 7, -1. And the parent function for t of x is x cubed. The chair function, that -2 is happening in the parentheses and also being raised to the third power. So that's a horizontal shift. To the right 2. And the +1 will be a vertical shift up 1. So the point that's at the origin, I go right 2, up 1, would leave me at 2, 1. The point that was at 1, 1 on the parent function, if I go right 2, up 1, lands me at 3, 2. The point that was at -1, -1, if we go right 2 and then up 1, lands me at 1, 0. And we can do additional points. I think 3 points is enough here. So those are a few examples of graphing when there's multiple translations that are happening to the parent function to give us the given function. All right, reflections. So if the parent function is being multiplied by a -1, it means we're ending up taking the opposite of each y coordinate from the parent function. That's going to end up being a reflection about the x-axis, or a vertical reflection. And then if each x is being multiplied by a -1, so if the input is being multiplied by a -1, that means that the graph is being reflected across the y-axis and ends up being a horizontal reflection. I like to keep them straight by thinking about the parent function y equals to x squared. So a vertical reflection to the parent function y equals 2x squared would be y equals to -x squared, written like so. And that would be each point from the parent function reflected over the x-axis, or vertical reflection. So 0, 0, 1, 1 would then be at 1, -1. -1, 1 would be at -1, -1. 2, 4 would be at 2, -4. -2, 4 reflected over the x-axis would be at -2, -4. 3, 9 would end up at 3, -9. -3, 9 would end up at -3, -9. And from your guys' Algebra 1 knowledge, you guys know that whenever the leading coefficient on the x squared term is negative, that's a parabola that opens down. So that makes sense here. Versus, let's switch colors. Let's do orange. If I wrote a horizontal reflection for the parent function of y equals to x squared, that would just be taking the opposite of each x coordinate. In this case, -x raised to the second power, well, that actually ends up simplifying to just be x squared. But if we think about performing the reflection, the point 0, 0 would stay in the same place. 1, 1 would end up at -1, 1. However, -1, 1 would end up at 1, 1. So nothing actually happens to the graph. And this goes back to what we talked about in sections 1.1 and 1.2 about how x squared, y equals x squared, is actually an even function, because the graph is symmetric about the y-axis, meaning a horizontal reflection doesn't do anything to the graph. Oh, I didn't label my graphs. Okay, so parent function for g of x, let's graph a few reflections. So the parent function for g of x would be absolute value of x, okay? And that negative on the outside of the absolute value bars means that each y-coordinate of the parent function ends up being multiplied by -1. So this is actually a vertical reflection. And then you think about every point from the parent function being reflected over the x-axis. 0, 0 stays where it is. 1, 1 goes to 1, -1. -1, 1 goes to -1, -1, and so on. Ooh, that was slightly off, huh? Okay, and the parent function for h of x is y equals to the square root of x. Notice that that negative is underneath the radical, so that's actually a horizontal reflection. So the point 0, 0 stays where it is. 1, 1 goes to -1, 1. And 4, 2 goes to -4, 2. And so on. So 9, 3 would go to -9, 3. And let's look at a few examples of some shifts and reflection. Okay, so the parent, let's do it, we haven't done like the red. The parent function for f of x is y equals x squared. And I'm going to list the shifts and reflections, so the translations and the reflections as they happen in order. So just reading the equation from left to right here, I can see that there is a vertical reflection, and that's from the minus out here. That +1 is going to be a horizontal shift, left 1. And then the -4 is going to be a vertical shift, down 4. So I think about the points on the parent function. So 0, 0, vertical reflection wouldn't go anywhere. Horizontal shift, left 1, and then down 4. Lands me at -1, -4. The point 1, 1, vertical reflection, lands me at 1, -1, and then left 1, down 4. -1, 1, vertical reflection, lands me at -1, -1, horizontal shift, left 1, and then down 4, 1, 2, 3, 4. Okay, and I can think about doing the same to some of the other points from the parent function. Nothing is happening to the shape of the graph. We haven't done any horizontal or vertical stretching. So it's just the graph of the parent function has been moved around. I'm just going to name it f of x. I'm not going to write the full equation on the graph because we'll get too busy. Okay, let's use green next. So the parent function for g of x is the square root of x. Now, you have to be careful with anytime something's happening to x. So anything horizontal, I just think you have to be extra careful and make sure you think about it for an extra moment. In order to see an actual horizontal shift, if something else is happening to x, whether it's a reflection or you'll see in the next part, a horizontal stretch or shrink, you have to factor out whatever is happening to x in order to see the actual horizontal shift. So the equation here needs to be rewritten by factoring out a -1 from underneath the radical. So factoring out -1, leaving us with the square root of negative and then times the quantity x plus 2. And then that plus 3 is still there. That means that there is a horizontal reflection and a horizontal shift left 2 units. Okay, and if I hadn't factored out that negative, I would have written down right 2 units, but it's actually left 2 units and then up 3. So the point that was at 0, 0, horizontal reflection wouldn't go anywhere, shift left 2, up 3. Okay, the point that would have been at 1, 1 for the parent function, horizontal reflection would be at -1, 1, and then we go left 2, up 3, landing me at -3, 4. And then from there, I can graph additional points, or I can think, okay, the point that was at 4, 2, horizontal reflection would be at -4, 2, left 2, up 3. Okay, so there's the graph of g of x. And the parent function for h of x is the same. Interesting, I wonder why I did that. Is the same, it's also the square root of x. And it looks like there is a vertical reflection. Ooh, notice, this is why I did this, that there is something happening to the x. We can see that there's a horizontal shift, but notice that that's -x. We need to make sure that we factor out the negative so that we can see the actual horizontal shift. So there's a vertical reflection, a horizontal reflection, then we're going to the right 3. So it's a horizontal here. I've been writing it out, so I'll write it out here. Horizontal shift. And a vertical shift down 4. Okay, so this is a bunch. The point that was at 0, 0 on the parent function, vertical reflection wouldn't go anywhere, horizontal reflection wouldn't go anywhere, horizontal shift right 3, and then vertical shift down 4 lands me at 3, -4. Okay, the point that was at 1, 1, vertical reflection, horizontal reflection, horizontal shift right 3, 1, 2, 3, puts me at 2, -1, and then vertical shift down 4 would put me at 1, 2, 3, 4, 2, -5. Okay,
Let's make sure that all of my points end up where they should. So the point 4, 2, vertical reflection lands me at 4, -2. Horizontal reflection lands me at -4, -2. Then right 3, 1, 2, 3 lands me at -1, -2. Down 4, 1, 2, 3, 4 lands me at -1, -6. And that looks like that's correct here. Okay, so these three were examples of graphing functions that have had horizontal and vertical shifts, but also horizontal and vertical reflections. And in part 2, we will start talking about some additional transformations, so vertical stretching and compressing.